Hello again. We finished up last time talking about vectors in 2 dimensions and how to add those and deal with those to some extent. And I wanted to today extend that into 3 dimensions. So we start looking at 3D. We're going to have those unit vectors like we talked about, I and j and k. Now we've added k to this, and that'll be the unit vector in the z direction. So if we look at a coordinate system, and we probably want to talk a little bit about this, it is a right-hand coordinate system. For our work here for a little while, it's not going to matter whether it's a right-hand system or not, but when we get into the cross product and crossing things, it becomes very important that we're dealing with a right-hand coordinate system. So let's talk a little bit about that. To see if it's a right-hand coordinate system, what you can do is take the fingers of your right hand. So take the fingers of your right hand and place them in the x direction and rotate them to the y direction, and your thumb should point in the z direction. So it's a little bit awkward, but let me try that again. Take your fingers of your right hand, put your fingers pointing in the x direction, and when you rotate them to the y direction, then your thumb should be pointing in the z direction. So that's the definition of a right-hand coordinate system, and we're not going to need it for a while, but I'm going to use it for a while so we get in the practice of always using a right-hand coordinate system. Well, let's say that I take this vector here and put it out into 3D or 3 space, and we can talk about it would cast some sort of a shadow on the xy plane. Would look like that, and we could even talk about this down here. We could, well, maybe I'll say that this is f prime, and we could talk about that. We'll take this as the given vector f. So if we pick up where we left off last time, we could say that this vector f was really equal to its projection on the xy plane, which would be f prime, plus the z projection. So if we look at that as z, we could just add z to this. So really, in what we're doing with the lecturing, going from 2 dimensions to 3 dimensions, we really are just adding the z dimension to it. You can see that there. Now if we talk about the y, there's f sub y, and there is f sub x. We could add those, making the substitution for that f prime is equal to fx plus fy. We could say then that this vector in 3 dimensions is equal to, substituting the f prime in there, fx plus fy plus fz. Now going and using our unit vectors, we're noting that I is in the x direction, j is in the y direction, ij, and then k is in the z direction. Again, k is just like I and j. It has a magnitude of 1 and represents simply a direction. So we could write this then as the magnitude fx in the I direction plus the magnitude fy in the j direction plus the magnitude fz in the k direction. So we've got magnitude and then the unit vector representing direction. So this would be a Cartesian form if you want. Well, if we look at the magnitude of this, we could say that f, which I guess we could write it like that, or I'll probably just start writing it like that, is equal to the square root of the magnitude fx squared plus fy squared plus fz squared. Now if we want to start looking at, we said this was a Cartesian form. If we want to start looking at a polar form with a magnitude, we need more than just one angle. So let's talk about that. Let me put another right-hand coordinate system here. And I'll put a vector here. Make the vector a little bolder so we can see it. So there is f. And I'm going to define these angles. If this is the x, this is the y, and this is the z, again a right-hand coordinate system. I'm going to talk about the angle here between the tail of the vector and the positive x-axis. I'm going to define that as alpha. Talk about the angle here between the tail of the vector and the positive y-axis. So these are the positive directions. So this would be beta. And then the angle between the tail of the vector and the positive z-axis, that would be gamma. Okay, so a little bit hard to see that gamma. It's the Greek gamma. If you go to the website under, I believe it's the miscellaneous tab, you've got a cheat sheet, a little helper sheet on Greek letters, and I'll try and post the link. Most of the time when I post the video, I post the link to that website, although most people come to the videos from the website. But just in case you happen here and you want to try and get back to that website, I'll post that in the notes on the video. So if we define these then, we're going to call them the coordinate direction angles. So the coordinate direction angles, alpha, beta, and gamma, is the angle between the tail of the vector and the positive axes. So if we look at this, if you think about it as the angle between the tail of the vector and the positive axis, this is always going to be alpha, beta, and gamma, always going to have to be less than or equal to 180 degrees. So it's never greater than 180 degrees, which hopefully makes sense. Now if we define those specifically, we look at the cosine of alpha. We're going to say by definition that is the x component divided by the magnitude of the entire vector. We could look at the cosine of beta, which is going to be the y component divided by the magnitude of the entire vector, and then the cosine of gamma, which is going to be the magnitude of the z component divided by the magnitude of the entire vector. So these are our direction cosines. Well, that's what they'll call them in math, and we can call them that. Or direction cosine. And if you thinking about breaking this up into a series of triangles, you can actually see this relationship. This is quite derivable. It doesn't just come out of thin air. Well, I would like to continue on with a little more theory here, and then we'll take all of that and apply that to some examples. So let me continue on and talk about the unit vector. We can talk about the unit vector u, which would be, if we take any vector, we'll take a force vector f, and we divide by its own magnitude. If you take something and divide by its magnitude, you really just get the direction. You've removed the magnitude from it. So that is the definition of the unit vector. If I rearrange this a little bit, I could say then that the vector f would be equal to its magnitude times the unit vector. And this is really hopefully nothing new here. If we take a magnitude and we append a direction to it, we of course have a vector. So when we go back to this one right there, if I write that a little bit differently, I could say that I have the unit vector is equal to, I could break this up, couldn't I? I could say that it was fx over f in the I direction plus fy over f in the j direction plus fz over f in the k direction, couldn't I? Looking at that. And we've seen fx over f, fy over f, and fz over f. Those were our direction cosines. So I make that substitution for that, and I could say that the unit vector would be equal to the cosine of alpha in the I direction plus the cosine of beta in the j direction plus the cosine of gamma in the k direction. Now if we remember Note that the magnitude, I'll write it there, the magnitude of the unit vector has to be 1, doesn't it? We said the unit vector had a magnitude of 1. So we can say then, if I look at the magnitude of the left-hand side has to be 1, what's the magnitude of the right-hand side? Well, that's fairly easy to ascertain. Cosine squared alpha plus cosine squared beta plus cosine squared gamma, that has to be equal to 1, doesn't it? The magnitude of this left-hand side setting equal to the magnitude of the right-hand side setting equal to the magnitude of the left-hand side. Now, if you wanted to square both sides, you come up with our final form here: cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. We'll put a box around that. So that's kind of handy. If someone gives you 2 of the angles, you can find the third. They give you beta and gamma, you can find alpha. They give you alpha and beta, you can find gamma if you want. So that's handy and something that we want to remember. Well, we've got quite a bit of theory on the table here. Well, let's go ahead and look at some examples. So we'll take an example here. Take this as y and z and x, and we'll say that we are given this force vector f. We're kind of given it in a little different sense. We're given each of the components here. So they tell us that the x component is 200 newtons. So we've got a metric problem here. The y component is 300 newtons, and they tell us that the z component is 600 newtons. I don't have great scale here, but I do have a right-hand coordinate system, so that's good. We'll take this as given. And what we would like to find then, I think it's important in your thinking to write down what's given, what's fine. That's proper engineering homework format. I'll try and keep that up here. It also clarifies our thinking. This is what we have to start with, and then this is what we're going to. Even if we can't figure out the solution, it's important to know what we're looking for. So we'd like to find the magnitude of f and the angles that it makes with x, y, and z. Okay. A lot of time I'll spend time writing things out because I want you to recognize them for what they are. What is the angle that it makes with x, y, and z? That's really to say we are looking for alpha, beta, and gamma, isn't it? So we want to recognize that. Well, let's see if we can do that. Do we have a, so our solution here is we've got fx, the magnitude fx, that's what? 200? 200 newtons. Fy, that's what? 300 newtons. And Fz, that's 600 newtons. So I could say if I wanted to write F in Cartesian form, it's really 200 in the I direction plus 300 in the J direction plus 600 in the K direction, and that would be newtons. I don't know that we were asked for that, but that's probably a good step in clarifying our thinking. What it was asked for is the magnitude of that. So we could say that that's really just equal to, if I've got it in that form, I know that it's going to be square root of 200 squared plus 300 squared plus 600 squared, which when the smoke clears on that should have 700 newtons. So we've got 700 newtons there. So we've got that part done. Also, it's important to come back here what we're looking for so we don't start celebrating, hey, we got that done, and forget there's more to this. We want other parts of it. Well, we'd like to find alpha, right? Well, we know from our definitions, the directional cosines, that the cosine of alpha is equal to the x component, which is 200, over the entire magnitude, which is 700. We know that the cosine of beta is equal to the y component, which is 300, over the magnitude of the whole thing, which we just found is 700. And finally, the cosine of gamma is equal to the z component, 600, divided by the magnitude of the entire thing, 700. So when you go through your math here, make sure your calculator is set up in degrees. We get alpha is equal to 73.4 to 3 significant figures. We get that beta is equal to 64.6 to 3 significant figures. And finally, gamma is equal to 31.0 degrees. So that would be our alpha, our beta, and our gamma. What does that mean then? Well, if I were to come over here and I mean, these are final answers. Draw some arrows. Be proud of these final answers. It's not asking for this, but conceptually, what are they talking about? Well, let me reproduce this coordinate system here again. X, Y, and Z. And we've got this vector out here, F, and what it's saying is that the alpha, that's this angle here, we know that angle is 73.4. Beta, that's this one here, 64.6. And gamma, there's gamma, 31 degrees. Okay, so that gives us some idea. We could locate that in three-dimensional space. Well, with all of these, normally when I have in a lecture with a class, I always ask these questions and we can go back over things, but I would encourage you, as you watch these videos, to hit the pause button, so to speak. See if you can go through this. While I would definitely probably print out the PDFs and follow along as I'm watching the videos, at some point I would probably also take the thing and cover up the work. Okay, we could take this, we could tear out a piece of the paper. Interesting to see how that'll sound on the microphone. But you could cover that up and see if you can rework the problem over there. I think sometimes it's very easy for us to stand here and go, oh yeah, that makes sense, that makes sense, that makes sense, and then we get to the examination that's a blank piece of paper and things don't make sense so much anymore. So back up on these, start out with a fresh piece of paper, hit the pause button, and see if you can work some of those problems too. So again, you've got to find the system that works for you. Well, with that, let's try one more example. Here we've got a couple more examples today. We'll see how this goes. So page number 4, let's say that we are given something like this. We've got some sort of a post or a column. And we've got a force that's applied to this. And there is a X. That would be X. There's Y. And there is Z, right-hand coordinate system. And we are told that the magnitude of that force is equal to 3 kilonewtons. Well, we've got a lot of metric problems today. We'll do both metric and English, rest assured, before we're done with this class. Beta is equal to 30 degrees, and gamma is equal to 75 degrees. Certainly the metric system is nice. You just get to move by the decimal place, but the real problem is I have no idea what 3 kilonewtons is. So conceptually, when we talk about 300 pounds, that's fairly large person, 3,000 pounds. That's a small car. 3 kilonewtons. We're not so used to that, so we have, at least I have a hard time with that. Anyway, we're given that information. We're given beta. We're given gamma, and we would like to then find. We'd like to find the magnitude of the x component, the magnitude of the y component, and the magnitude of the z component. Okay, let's see if we can do that. We're given beta and gamma. I bet before we're done we're going to need alpha, so let's see if we can get that. We know that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1, right? Well, if I substitute in my beta at 30 degrees and I substitute in my gamma at 75 degrees, I come up with alpha that's equal to 64.7 degrees. So that was not asked for, but that will probably be a useful intermediate step. So then I could recognize that cosine of alpha is equal to fx over f. So I could say that fx is equal to f times the cosine of alpha. Do we have f? Yeah, we have f, 3 kilonewtons, times the cosine of alpha, cosine of what we found there. I'm glad we found that. 64.7 degrees. We put that right in there, and that turns out to be 3 kilonewtons times cosine 64.7, 1.2 kilonewtons. So that's the magnitude of the x component. Well, we could just continue through this. We've got the cosine of beta is equal to fy over f. So we have fy is equal to, let's see if I get that right, beta, fy over, yes. Fy is equal to f times the cosine of beta, which is equal to 3 kilonewtons, times the cosine, where's beta? Right up there, 30 degrees. Which then we can say that fy is equal to 3 kilonewtons cosine 30 degrees, 2.6 kilonewtons. And finally we could say that the cosine of gamma, which is defined as f sub z over f, you could say then that f sub z is going to be equal to f times the cosine of gamma, which is 3 kilonewtons times the cosine. Do we have gamma? Yep, 75 degrees. So we've got then fz is equal to, the magnitude fz is equal to 0.8 kilonewtons. Got that right? 1.2, 2.6, and 0.8. Now before we run off, we probably want to check on this. They seem reasonably right. I mean, none of them's larger than 3 kilonewtons. That's probably a good check. All of these angles are positive, so and less than 90, so I'm going to, well, by definition they have to be less than 180, but they're less than 90, so I'd expect the components to be in the positive direction. I think that is okay. How could I test to make sure I don't have a mistake there? We could look at the magnitudes and see how they add up, right? Okay. Well, didn't we say our directional cosines had to be less than or equal to 180? I believe so, yeah, by definition. So they're less than or equal to 180. I think that's good. We have, as I said, they're less than 90, so we know we've got positive components on these. Well, let's check this out. What if I were to, we'll just carve out a little space here. This is our check. Look at the square root of 1.2 squared plus 2.6 squared plus 0.8 squared. And when you go through that, you come up with 2.97, which is pretty close to 3, isn't it? The only difference there is the round off. If I were to have more significant figures or keep them in the memory of the calculator here, I would have come out a little better. But I think we can have confidence that we've got the right answer. And it's probably important to think about. A lot of times people get all excited about the decimal places. They want to talk about 4, 5, 6 decimal places. I'm more interested in the left-hand side of the decimal place. There's a phrase that didn't start with me, but I like to repeat it. It's better to be approximately right than precisely wrong. I like to step back from a problem and say, is this about right? Okay? Are all of our answers less than 3? Does it seem reasonable? And I'm going to implore you to ask those questions throughout the term and throughout your education and on into your career. Because while some people are worried about way out here, you know, what's the next significant figure and whatnot, I am usually most concerned about the left-hand side of the decimal place, again, to be approximately right rather than precisely wrong. Well, that hopefully was a good example. Let's, what are we doing on time? Well, I think what we will do is we'll try one more problem here and wrap up lecture then. So let me look at a coordinate system here. So I've got X, I've got Y, I've got Z. Again, a right-hand coordinate system. And I'm going to show a couple of vectors here. Okay, this is F1 that we'll say is 80 pounds. And there's an angle here. So its elevation angle from the XY plane is 30 degrees. And its angle to the x-axis, that angle there, is 40 degrees. Okay, that's a little hard for students to get sometimes, so we'll go through that. Then we've got this vector here. This one's a lot easier if you're going to do group study. You want to talk about F2, which is straight down the negative z-axis, 130 pounds. So we've got a English set of units. We've got this that's given. And we'd like to find F1 and F2 in Cartesian form. And the magnitude along with alpha, beta, and gamma for the resultant. Okay, so the plot's thickening. We're going to define F1 and F2 in Cartesian form and then find the resultant in magnitude angle form. And remember, resultant is really the sum, so we're going to add F1 to F2. Well, like I said, if you're going to do group study, the one you want to volunteer for is F2. Now, maybe you want to volunteer for F1. Maybe you like challenge. But if you're kind of a slacker, like to take the path of least resistance, you want to volunteer for F2. That's going straight down the negative z-axis. This is minus z down here, isn't it? So I could just say that this is, and if we want to be very complete, 0 in the I plus 0 in the J minus 130 in the K, and that would be pounds. So I'll go ahead and say that F2 is minus 130 K, and we should put units there. So if we want F1 in Cartesian form, that's done. I mean, not F1, I'm sorry, F2. Well, F1's a little more work. What I'm going to have to do is I'm going to have to look at the projection of this on the XY plane. That's that piece right there. And then translate that into X pieces and Y pieces. So to do that, I'm going to have to say that I have F1, which is going to be, if I look at this piece here, That's going to be 80 times the cosine of 30. That gives me the length of this shadow on the xy plane, and then I need to find this distance there, which is going to have to be multiplied again by the cosine of 40. And that's the eyepiece. Then I do this again. I have 80 times the cosine of 30. Again, that gives me this piece along here. And now I need to find this piece here, so I'm going to multiply that by the sine of 40, right? And that's in the j direction. Now this was in the positive x direction. This one points this way, so that would be in the minus j direction. And finally I have the z direction here, which is going to be positive 80 times the sine of 30, and that would be in the k direction. Okay, so 80 sine 30 in the k. Now let me go into that in a little more detail, because I realize this often causes problems. Really, I have a triangle that looks like this, where this is 30, this hypotenuse is 80, and that's a right angle. That's this triangle that you see right here. Okay, and then I have this triangle here, where this is the x piece, this is the y piece, this is now the right angle, and that is, this angle here is the 40. Okay, so when I say 80 cosine 30, that gives me this side here. Then when I say the cosine of 40, that gives me whoops, I've got these wrong. Better do some erasing. This is the y piece here. Sorry about that. There's the y piece there, and this is the x piece. Rookie mistake there. Okay, so I've got the x piece coming out here. So now, again, this line, the shadow line on the xy plane, that's 80 times the cosine of 30 gets me that. And then if I want x, I have to multiply that piece times the cosine of 40. Now if I take this 80 cosine of 30, that's that piece, and I want this y piece, what do I have to do? I have to multiply by the sine of 40. Now the z is the easy one, because all I have to do is do 80 times the sine of 30. So these two are a little trickier because you have to use two right triangles. Two right triangles. Well, those are your components. When you grab your calculator and get through those, you end up with F1 as 53.1 in the I direction, minus 44.5 in the J direction, plus 40 in the K direction. And that would be pounds. So 53.1 minus 44.5 plus 40. Does that make sense? They're all less than 80. That's good. The z is positive. The x is positive. The y is negative. That seems reasonable. Okay. So if I want the resultant, I can say then that the resultant is really just equal to F1 plus F2. I can take these, I add the i's to the i's, j's to the j's, and the k's to the k's, and I will come up with 53.1 in the I direction minus 44.5 in the j direction. Easy so far. I'm going to take minus 130 plus 40 gives me minus 90 in the k direction. Okay, now I'm not going to underline that because that's not a final answer. I mean, if we wanted the resultant in Cartesian form, we would be done. We don't want it in Cartesian form. So I'm going to have to go a few more steps. So here we are here. I think we can fit this in. So I'm going to say then that the magnitude of f sub r, that would really be just as easy as taking the square root of 53.1 squared plus 44.5 squared, and the math folks will be upset. That should be minus 44.5 squared. We put the negative sign inside there. Of course, it's going to go away. Normally, I'll just write it as 44.5 squared, and then plus 90 squared. You see, I know that a negative will go away when I square it. So when I do that, I come up with 113.6 pounds. That's our magnitude, isn't it? Okay, 113.6. So I got too many significant figures there. I should probably stick with 3. It'll be 114, but that gives you something to compare your work to. Then I can say that the cosine of alpha is equal to fx over f, which is going to be equal to what? 53.1 divided by 113.6. So alpha, solving for alpha there, we'd basically take the arc cosine of that piece, wouldn't we? Alpha turns out to be equal to 62.1 degrees. Okay. The cosine of beta is equal to fy over f, which is going to be minus 44.5 divided by 113.6. Okay, so you could say then, I mean, if you wanted to, you could say that beta is equal to the arc cosine, the inverse cosine of minus 44.5 over 113.6, which turns out to be equal to 113.1 degrees. Seems like an odd answer. Let me grab the calculator and double check that. Yeah, that's correct. So the one thing you have to be careful of here, while I was a bit flippant with the negative signs here, really I should have had this this negative sign right there when I squared that, although when you square it, it goes away. I was not careless here. I made sure I put that in, because if you don't put that in, you're going to get the complement of this angle. So be careful of that. Make sure that you include that. Well, let me then finish up. The cosine of gamma is equal to fz over f, which would be what? Minus, I've got to be careful to put the negative in there, the minus 90 divided by 113.6. So you get that gamma is equal to the arc cosine of minus 90 over 113.6, which nets me 142.4 degrees. And double check that one for you too. Yep. Okay. Well, if you wanted to, I think we're okay. We've found F1 and F2 in Cartesian form. We've got the magnitude and the angles for the resultant. One thing we could do if we wanted to is we could check out this work. What is the cosine squared of alpha, 62.1, plus cosine squared of beta, 113.1, plus cosine squared gamma, 142.4. What's that turn out to be? I haven't done this calculation, so I'll run through it on the calculator, give you time to do the same if you want. So I end up with 1.00, and I actually did key these in, 1.006, which is just about 1, isn't it? Which is what it should be. So It's always good to look at the numbers. Do they make sense? Are they reasonable? And do some checking to make sure that you haven't made a mistake somewhere. Is this conclusive? No. I mean, you could have answers that pass that weren't the right answers. But it is if you come up with this, it's very quite a bit less likely that you've just made a decimal mistake or something like that. So anyway, that wraps up our work for today and for the first week. And when we get together next time, we're going to continue on in Chapter 2. We're going to talk about position vectors and work in 3D. And so take care till then, and thank you for listening and watching.